Hello everybody. In this video, okay, good, there's a little bit more light. In this video I want to go through the proof of those sum and difference formulas that I just kind of gave you before, and I just want to go through why they work and why they are valid. So what I first want to start with is a picture of what cosine u minus v actually means. So let's write that out. Let's say proof, first of all, proof of, I just wrote W, meant U, of sum and difference formulas. My goodness, formulas. Okay, wow. Sorry, apparently not very awake here. Okay, so to begin, let's draw a picture of what cosine of u minus v actually means. So we'll write that out. Cosine of u minus v. Remember, it's an angle minus an angle, right? So if we draw that on the unit circle, we first should draw our unit circle out. Okay. Over here, to begin with, we always have that quadrant angle at 1, 0. And we're going to label this point A. And the first angle we can talk about is U. So let's say we have some larger angle here, U. So I'm going to start here. I'm going to go around counterclockwise. And I'm going to stop at some arbitrary place, just let's say like right here, right? And I'm going to draw a line out to the edge of my unit circle. And I'm going to call this inner angle here U. And I'm going to label that point D. And then let's say that I had another angle in here, V. Let's say I had angle V. So draw another line out, draw an arrow describing that angle, label it V, right? And we'll call that point B. And then somewhere in the middle here, right, if I took this whole angle U and I subtracted this V from it, I'd probably be somewhere around here, right? Here's my line out. And I would have an angle in here. I'm going to draw another arrow describing that. And this angle I would call U minus V. Okay. And that angle represents, right, the distance between this angle U minus this angle V. And it would be somewhere around here. And I'm going to label that point C. And what I want to label further now are the points B, C, and D. Because even though I don't know what they are, I can still give them labels. I can label them X1, Y1 here at B. I can label them X2, Y2 at C. And I can label them X3, Y3 at D. And furthermore, what I want to remind you guys of, this will be important later on in the problem, what I want to remind you of is that if I have a coordinate on my unit circle like this, that means I also have a cosine and a sine, right? So what I have here at x sub 1 is cosine of that angle. Cosine, this angle we called V, so this is actually cosine of V, and y1 is sine of V. And over here at U, right, at point D, that means x sub 3 is actually cosine of U, and sine of U is y sub 3, right? Because this angle is U, so it's cosine of U, sine of U. This angle is V, so it's cosine of V, sine of V. And just like before, right, at this U minus V angle, whatever it is, I also have sine and cosine of that angle. So my x sub 2 can also be talked about as cosine of U minus V, and my y sub 2 can also be talked about as sine of U minus V. Okay, so this is really just a visual of a representation of what cosine u minus v is. And from what we've set up here, we can actually start to talk about some really interesting things. First of all, I want you guys to understand and just kind of remember, on the unit circle, my radius is always 1. So that means this line segment here from the center of the circle to B is 1. Center of circle to A is 1. Center of circle to C, 1. Center of circle to D, right? 1. They're all the same length. So let's draw another picture to kind of illustrate what happens there. So once again, same circle. And just like before, right, my B was about right here. Same circle, I just am not drawing the same lines in, but it's the same thing. Here was A, B was here, C was roughly here, and D I had right about here. Okay. And like I talked about, right, like I just was mentioning to you guys, the line segment from the center to any of these points is going to be 1. So here's what I can conclude about the distance then between A to C and B to D. I know that from C to the center and A to the center, right, those are the same distance. So check this out. Put a little tick mark in each of those lines because we know they're the same length, and then draw a line from C to A. And you can see we've drawn a triangle in here. And what we can conclude here is that I've made an isosceles triangle. This segment here is 1, this segment here is 1. These are the same length, and so I've made an isosceles triangle. And I can actually recreate that same exact triangle if I do the same thing from D to B, right? I know D to the center of the circle is 1. And I know B to the center of the circle is also 1. And I made these like a little bit hard to see the triangle, but I'll do my best to kind of draw the picture out, right? That means that this length of the triangle, this length of the triangle is the same, and so this base of the triangle, right, my dashed line here, is actually the same exact length as this line from C to A. It's the same triangle, right? Distance of 1, base. Distance of 1, and the base. So, what I can say then in words, right, kind of using algebra to write that out, is that the length of this segment here, DB, is equal to the length of A to C. And so, what I can furthermore fill in there is using the distance formula, those coordinates that I talked about earlier. So here we go. I can write out D, B, and AC in terms of the distance formula because, again, these are also coordinates, right? I'm going to write those again. D was the coordinate, x sub 3, y sub 3. B was the coordinate, x sub 1, y sub 1. C was the coordinate, x sub 2, y sub 2, and A was the coordinate 1, 0. So, what I can express now is dB in terms of the distance formula, right? If I fill these in, these two coordinates in, and same thing with AC, I can express it in terms of the distance formula if I fill in for my coordinates. So here is what that would look like. Right, I'm going to remind you, just a quick recap, review over here on the right, what the distance formula is, because it may be something that we've forgotten. The distance formula is the square root of y2 minus y1 squared plus x sub 2 minus x sub 1 squared. And so for dB, right, for dB, my x sub 1 is x sub 1, so I'm going to start by writing that. My x sub 1 is x sub 1, my y1 is y1, but instead of writing my y2 and x2, I'm going to write that with the 3. I'm going to use that as my second coordinate. So my first thing I'm going to write is y sub 3 minus y sub 1 squared plus x sub 3 minus x sub 1 squared. And that represents dB. For AC, I can fill in 1, 0 is going to be like my x1, y1, and x2, y2 is going to be like my x2, y2. Right? That part I don't have to change. So again, I set up my square root, and I say, okay, my y2 is y2 minus my y1, which is 0, squared. And then I say plus, and I do x sub 2 minus 1, and I square it. And now what I've done is I've expressed dB and AC in terms of the distance formula. And what I've created for myself here, first of all, is a radical equal to a radical. So the first step I could take here is essentially squaring both sides of this and getting the following equation. Right, the radical just goes away. And so I fill in everything as it is, but without the radical on top. And now I have something to FOIL out here, right? I can FOIL out this binomial, I can FOIL out this binomial, and I can FOIL out this binomial. So that's what's going on here. I'm going to write out that step, but I'm not going to write out all the algebra it would take to do that. That's really tedious, and it's basic algebra skills. It's really not something you need my help with at this point, but I will show you the step that's missing. And the actual algebra of foiling out, I'm confident we can manage on our own at this point. And over here, y sub 2 squared is exactly that, y sub 2, and then I say squared. If you want to leave like a little bit of distance between the squared and your y sub 2, that would be a good idea, so you don't get confused about what that means. Or you can even use parentheses, y sub 2 squared. Plus, and remember I have to FOIL out that last thing, x sub 2 minus 1, and I would FOIL out those things. So that's what I'm doing in this step. But again, I'm not going to go through multiplying every little thing with you. I am just going to show you what all of that would be simplified. Alright, so what we can write out then for all of our terms is the following thing. On the left side of the equation, I'm going to get x sub 3 squared minus 2 x sub 1 x sub 3 plus x sub 1 squared. And then I'm going to get plus y sub 3 squared minus 2 y sub 1 y sub 3 plus y sub 1 squared. That is the left side of my equation. Equals, and on the right side, I'm going to write kind of below this because I'm sort of running out of room on the paper here. On the right side, I'm going to get x sub 2 squared minus 2x sub 2 plus 1 plus y sub 2 squared, right? That y sub 2 squared just kind of stays there. It gets tacked on at the end. And here's an interesting thing that we get to do when we start talking about all of these x sub 2 squares, right, y sub 2 squared, all of these x, y values squared. Let's go back to the unit circle for a second. Let me draw you just a quick picture. So again, imagine we're here on the unit circle. And let's say, oh, here, now you can see it. It's a little bit better. If we have any line segment on the unit circle, right, that extends out, we have a coordinate x something. I'm going to call it I, and y sub I. It could be any number that I fill in there, right, just like we kind of did. What I want you guys to understand is because we know that this side length here is 1, what we can do is we can describe the rest of this using the Pythagorean theorem. So, right here is x sub I, and right here the height is y sub I, right? That's how we get that coordinate. It goes out this much and up this much, makes that coordinate x, y. And these lengths can be expressed in terms of 1, right, if I square them using the Pythagorean theorem, right? I can express this length of 1 if I say, okay, x sub I squared plus y sub I squared is always going to equal 1 on the unit circle, right? Any one of these right triangles has a hypotenuse of 1. So their x squared plus their y squared has to follow the Pythagorean theorem, right? Has to equal the hypotenuse of 1. So what I'm going to do next with my problem is I'm going to group together all of these x's and y's that are squared, because when I group them together like that, they're all going to be 1 when they all have the same sub number. So here's what I mean. Let's group them together first, and then I'll explain what I'm doing. When I group together on the left side, I'm going to group together my x sub 3 squared and my y sub 3 squared. I'm going to probably put those in brackets. Alright, so that's crossed off now. I talked about my y sub 3 squared and my x sub 3 squared. And then I'm going to add my x sub 1s, right? My x sub 1 squared and my y sub 1 squared. Take care of those. And then I get to write the last two terms on the left side. Negative 2x1, x3, negative 2y1, y3, and that's the left side of my equation. And on the right side, I can really only group the x sub 2 and the y sub 2 squared. So what I can write, again, I'm just going to write a little bit below, is x sub 2 squared plus y sub 2 squared minus 2x sub 2 plus 1. Now, like I just talked about, every one of these sets of brackets is really equal to just 1, right, using this Pythagorean identity here. Formula, I guess property, it's just something that's going to be true every time for a unit circle. And it's true for every single pair of these x's and y's. So I can replace every single pair of these x's and y's with just 1. So I'm going to do that next. I get a 1 plus a 1 minus 2x1, x3 minus 2y1, y3 equals 1 minus 2x sub 2 plus 1. And of course I combine my like terms. Right, I get 2 minus 2x1, x3 minus 2y1, y3 equals, again, combine like terms, 2 minus 2x2. And now I'm hoping we see what the glaringly obvious factoring that needs to happen here, and that is factoring of the 2 on either side. So every term here has a 2. I get 1 minus x1, x3 minus y1, y3 equals a 2 outside 1 minus, x2. And then I can divide by 2 on both sides to really just move that thing out of my whole equation. Let me get some more room here. And then what I get is 1 minus x1, x3 minus y1, y3 equals 1 minus x2. And when I try to move these numbers over, right, I would subtract 1 here and subtract 1 here, and that would actually make the 1s completely go away. And I'll just write that step in. Your book misses a lot of the algebra, just kind of skip steps, so I'll do you the favor of showing you those steps right now. And then what I end up getting is my negative x1, x3 minus y1, y3 equals negative x2. And again, a basic property of just solving equations. If I have everything negative, I'm really allowed to change the sign. If I change the sign of one side, I'm allowed to change the sign of the other. So I can make this x2 positive equals positive x1, x3 minus, or pardon me, plus now, y1, y3. And it seems like that's kind of all we can do, but what we need to remember is what we wrote down at the very, very beginning of this video. We gave another name for all of those x2's, x like x sub 1, x sub 2, x sub 3, right? We actually labeled according to cosine and sine, right? x1 was cosine v, y1 was sine v, right? Remember all of those sine and cosine names? We gave all of those coordinates. We're going to use those now, and we're going to fill them in. So, x sub 2 we called cosine of u minus v. X sub 1 we called cosine v. X sub 3 we called cosine u, plus y sub 1 we called sine v, and then y sub 3 we called sine of u. And there you have it. We've arrived at just one of those sum and difference formulas. But remember how these work. This is true even if I do like plus minus, correct? What I can say furthermore here is, because this formula is the same when I add it, I just change the sign. Cosine v still, cosine u still, I just make it minus. It stays exactly the same. I can really call this formula, I can kind of just condense it into one as cosine u plus minus v equals cosine v cosine u plus minus sine v sine u. And vice versa. That is definitely what we're allowed to do here. And with the sine formulas, right, I can do the same thing. So I can say, all right, then sine of u plus minus v is equal to sine u cosine v plus minus sine v cosine of u. And what we can do from here is use this cosine and sine sum and difference to prove tangents sum and difference. So just like everything else involving tangent, right? Tangent is always sine over cosine, right? So tangent u plus minus v, of course, starts as sine u plus v plus minus v over cosine u plus minus v. And like we just talked about, what we're allowed to expand those both out as are their sum and difference formulas. So I can call sine u plus minus v sine of, well, I guess it doesn't matter which goes first, but sine of u cosine v plus minus sine of v cosine of u. And I can put that over cosines, sum and difference, which says cosine v cosine u plus minus sine v sine u. And what I can do from there is divide everything by cosine, cosine u, cosine v. So I can divide the numerator by cosine u, cosine v, and I can divide the denominator as well, same thing. By cosine u cosine v. And I can break apart both of these fractions, right, because it's two things over one denominator, two things over one denominator. So the next thing I can write is my first numerator over cosine u cosine v, plus minus in the middle, and do it again. Sine v cosine u. Right, just breaking up that top fraction. And the bottom fraction doing the same thing. Putting each part over cosine u cosine v. It's going to take a little bit of writing to get there, but we can get through it. All right. I have my sine v sine u over cosine u cosine v. And now what we can start to do is simplify, of course. So the first thing we should see here in the numerator, this first fraction, is the cosine v and the cosine v. They cancel each other out. They become 1. And same thing over here, cosine u, and I get sine v over cosine v. Here on the bottom, notice these are actually both the same. Cosine v, cosine u, and I get just the number 1. And we also get to simplify our last part as two separate fractions. I want you to understand it's actually sine v over cosine v and sine u over cosine u. So I'm going to kind of rewrite that so it's a little bit more clear. I'm going to say, okay, that's actually sine v over cosine v times sine u over cosine u. And now that we've made everything really clear, we're going to rewrite. So, first things first. Sine over cosine we know is tangent, and the argument is u. So it's going to be tangent of u plus minus. Over here, same thing. Sine over cosine is going to be tangent, but the argument is v. So it's going to be tangent of v. And on the bottom, on the left, I have 1, and I have plus minus. And then I have these two fractions we wrote up before, right? Sine v over cosine v. That, again, is going to be tangent v. Times, over here, sine over cosine, but the argument is u. That's going to be tangent of u. And again, I've arrived at the other fundamental sum and difference formula, tangent sum and difference formula. And that's all the proving I have for you in this video. So, thanks for watching.